Have you ever wondered what gives a firework its incredible bang? Or maybe how an instant cold pack gets icy cold just by squeezing it? Well, the answer to both is actually the same thing. It's all about a hidden world of energy that's stored inside molecules. And in this explainer, we're going to unlock.
I mean, just look at that. That dazzling light, the powerful boom. All of it is energy that was just sitting there, locked away inside the fireworks chemicals, and now it's being released. But how? Well, it's a fundamental process, and by the time we're done here, you're going to see exactly how it all works.
So here's our game plan. We're going to break it down into 4 simple steps. First, we'll look at the 2 main types of reactions. Then, we're going to pop the hood and see the 2-step energy process that's going on inside. After that, we'll get our hands dirty with a really simple analogy, and then finally, we'll learn how to actually keep score of all this energy change. Let's dive in.
Okay, Section 1. Explosions and cold packs. This is all about the 2 basic ways chemical reactions deal with energy. They either give it away or they take it in. It's one or the other.
And we've got 2 great words for this. First up, exothermic. Just think exo for exit. Energy exits the reaction. It releases energy, making everything around it feel hotter, like our firework. The opposite of that is endothermic. Think endo for enter. The reaction has to pull energy in from its surroundings, which makes things feel cold. And that's your instant cold pack.
And here are some fantastic real-world examples. A burning candle? It's literally giving off heat and light. That's a classic exothermic reaction. Now look at the ice cream. For it to go from a solid to a liquid, it has to suck heat in from the air around it. That's an endothermic process right there. It's pretty simple when you see it like that, right?
So we know reactions can get hot or cold. But why? In this next section, we'll see that what looks like a single event is actually a 2-step dance, a kind of energy trade-off that's happening inside every single reaction.
Which, of course, brings up the big question. Where is this energy actually being stored and swapped around? It's not just floating in the air. It's locked up somewhere very, very specific. And the answer is in the chemical bonds. Those connections that hold atoms together to make molecules. You can think of them as tiny little warehouses for energy. And here's the absolute key. Every chemical reaction is really a 2-part story. First, you have to break the old bonds, and then you get to make new ones.
Now, this is the part that might seem a little backwards at first. Check it out. Step 1, breaking bonds, always takes energy. You have to put energy in to pull things apart. It's step 2, making the new bonds, that actually releases energy.
And that leads us perfectly into our 3rd section. To really get a gut feeling for this whole energy in, energy out thing, we're going to use a super simple analogy that I think makes it all just click into place. Legos.
I want you to imagine you have 2 Lego bricks stuck together. You have to use effort, right? You have to put energy in with your fingers to pull them apart. That's bond breaking. Now, think about snapping 2 new bricks together. You get that satisfying click, that little bit of force. That's energy being released. That's bond making. So remember, it costs energy to break things, and you get energy back when you build them.
In chemistry, we actually measure that effort. We call it bond energy. It's the specific amount of energy you need to break 1 mole of a certain kind of bond. And what's really cool is that it's a perfect 2-way street. The energy it costs you to break a bond is the exact same amount of energy you get paid back when that same bond forms.
And, of course, not all bonds are made equal. Just like with Legos, some connections are way stronger than others. A carbon-carbon single bond, for instance, has a bond energy of about 350 kilojoules per mole. But a carbon-oxygen double bond, whoa, that's way stronger. That's 740.
All right, last section. We've got all the pieces on the board now. Bond breaking costs us energy. Bond making gives us energy back. So now we can finally put it all together and create an energy scorecard to see if a reaction is a net win or a net loss, energetically speaking.
The official, sciencey name for this scorecard is enthalpy change. We use the symbol delta H. Now don't let the name intimidate you. Enthalpy is just a fancy word for the total heat energy in a system. And that triangle, delta, is just a symbol that means change. So delta H literally just means the change in heat. It's our final score. So how do we calculate it? Well, the formula is beautifully simple.
The overall change is just the total energy you spent breaking the old bonds minus the total energy you got back from making the new ones. It's that simple. Energy in minus energy out.
And these energy diagrams show us the only two ways it can go. Look at the one on the left. If it costs more energy to break the bonds than you get back, then your final products end up at a higher energy level. Delta H is positive and the reaction feels cold, it's endothermic. But if you get a huge energy payoff, like the diagram on the right, the products end up at a lower energy level. Delta H is negative and the reaction gives off heat, it's exothermic.
So doing the actual math is a really simple three-step process. Step 1, add up all the energies of the bonds you have to break. That's your total energy in. Step 2, add up all the energies of the new bonds you're going to form. That's your total energy out. And step 3, just subtract the out from the in to get your final score, your delta H.
Let's look at a quick, real-world example, making ammonia. It takes 2,252 kilojoules of energy to break all the starting bonds in nitrogen and hydrogen. But when the new bonds in ammonia form, they release 2,340 kilojoules. So because more energy was released than was put in, the overall change is negative, and the reaction is exothermic. It literally produces heat.
So if you only remember one thing from all this, let it be this. From the fuel burning in a car to the food you eat, every single chemical reaction is just a story about treating energy. It's an investment of energy to break old bonds, to pull apart those Legos, for the big payoff you get when new, more stable bonds snap together.
And that brings us right back to you. The process of respiration that's powering your body this very second is a constant, steady exothermic reaction, breaking down glucose to release the energy that keeps you alive, keeps you thinking. So, my final question for you is, what other energy reactions are happening in and around you right at this moment? Think about it. Thanks for joining me on this one.